Good evening, everybody. I know you guys are glad to be back here after your long weekend, right? And also welcome to another session of organic chemistry. Of course, you know, yeah, go ahead. Are you saying something? Go ahead. Okay. Okay, anyway, so we are going to finish chapter 1 today, and of course, before we start with chapter 1, we are going to do those problems that you guys have just finished in the quiz that you have just taken. But before we do that, let me make a couple of announcements. Tomorrow, that is August 29, is that correct? Wednesday, August 29, at 8 p.m., we are going to have our first online review session. Online, that will be live session. That is tomorrow at 8 p.m. I will send you the link to that session. And tonight, I will send you the link tonight. And then tomorrow, I will also remind you of that session tomorrow. For the session tomorrow, for the online session, we are going to use the OWL chapter 1, end of chapter 1 questions for the session tomorrow evening. So I hope to be able to see all of you there tomorrow at 8 p.m. Okay, now, to finish up with chapter 1, like I said, before we do that, there is a couple of summary definition I want to share with you before we do the problem set. Remember, before we left, most of the time we have discussed valence. I want to bring this up because these are very important concepts. Valence. I want to give you a summary definition of valence, which is the number of electrons needed by an atom in order to attain an electron octet in a stable molecule. This is a very important concept indeed, because as we go along during the course of this semester, we are going to continue to come back to this concept. This is the number of electrons that an atom needs in order to attain an octet of electrons. Another definition that you could also use for valence, you could also say this is the maximum number of bonds, maximum number of covalent bonds for an atom in a stable molecule. So those are the two different ways in which you look at valence. So therefore, if I ask you, what is the valence of oxygen? What is the valence of oxygen? What is it? Valence of oxygen. 2. Keep in mind it is the number of electrons that it needs in order to attain the octet of electrons, right? Valence is different from valence electron. There is a slight difference between them. That is why I think it is very important I bring this up. So therefore, if I ask you, what is the valence of nitrogen? 3, exactly. About chlorine? 1. Okay, so let me just summarize for you. Valence for carbon is 4. Oxygen is 2. Hydrogen, in the case of hydrogen, all it needs is 2 electrons, so it's 1. The halogens, which is the chlorine, bromine, halogen is 1. These are the chlorine, bromine, iodine. Nitrogen is 3. Okay? So it is very important that you know all of this. Okay. Now, another concept that I would like to give you a summary definition, of course, is octet. We all know the octet rule. That is the need for an atom to surround itself, with 8 valence electrons in a stable molecule. In a stable. Notice I keep saying stable because sometimes an atom may violate the octet rule. Could very well mean that that atom, the molecule is not stable, in a stable molecule. So these two concepts, valence and octet, make sure you know them, okay? Because as we go along during the course of this semester, we are always going to come back to these two concepts. Okay, having done that, let us now do the problem set in today's quiz. Okay. Okay, Donette, can you read the first question for us?
What is the ground state electronic configuration of sulfur?
Okay, what is the ground state electronic configuration of sulfur? Yes. C? Okay, very good. How many people agree with that? Everybody. Okay, why do you say it's C? Very good. Okay. So there are two ways in which you could take a look. That's good, by the way. Very good. I mean, you could approach this here by looking at the number of valence electrons. Okay, you know sulfur has 6 valence electrons. And if you look at this molecule here, this is the only electronic configuration in which you have 6 valence electrons. So that means that that would be sulfur. You could also look at it from the point of view of atomic number. How many electrons does it have? What is the atomic number of sulfur? 16. If you look at it from that point of view, you also find that you have 16 electrons here. Okay? Okay, so that is correct. C is the answer. Now, even though that is the answer, let us do A. What is A? Which atom is A? Which atom is A? Aluminum. Okay. How many people agree? Okay, that's aluminum. Very good. Okay, let me erase this. About B, what is B? What is it? Silicon. Very good, very good. You guys are becoming experts. Okay, of course, we all know that C is sulfur, right? Okay, which is the answer that we want. How about D? What is D? Chlorine. Exactly, good. Okay, that's good. So we don't need to do, I don't need to review that with you guys. I know that you know that now. You know the electronic configuration now. About 2, let me see. Do I know anybody here? Is Mitchell here? No, you should sit down here. No, it's not here. Ogechi. Okay, since I know your name now, so read number 2 for us.
Okay. Which of the following molecules has the sp3 hybridized carbon atom?
Okay, which of the following molecules has sp3 hybridized carbon atom? Before we do that, let me help you out a little bit. Let me help you out a little bit. And what I'm going to do here, I'm going to write out the structure of each one of these molecules. For example, this here, which is ethane, one of the components of your cooking gas. Yeah, bless you. Okay. So the structure for ethane is this here. You have 2 carbon atoms joined together. Of course, we are going to discuss writing structures in organic structures very shortly. But for now, let me show you this. That is the structure of this here. For this, that is the structure here, double bond. That is ethylene. Okay. For this here, this acetylene, that is what you use in acetylene touch. The structure is this. It's a carbon-carbon triple bond. And finally, this here, formaldehyde, this is what is used to preserve biological samples. It's called formaldehyde. You have hydrogen bonded to carbon, and this is a carbon-oxygen double bond. Let me do that better. Okay, given that now you know the structure of all of this, the question is which one has sp3 hybridized carbon? A? Okay, why do you say A? A is correct, by the way. That is correct. Why A? Because the carbon is bonded to 4 atoms. Very good. 4 atoms. Very good. So that is sp3 carbon. Now, what is the... Okay, so this is correct. What is the hybridization of this here, since we are of each of the carbon here? sp2? Okay, great. So we don't even need to do that anymore. Okay, about this one here? About this one here? sp2 also, very good. Okay. So far, so good. Take this out. You can say this molecule here is called formaldehyde. Okay, what is the hybridization of this carbon here? sp2. Okay, very good. Now I was going to ask you what is the hybridization of the oxygen, but I will wait until the end of, in about 10 minutes from now, I will ask you that question, because I don't think you can answer that yet. Okay, so the hybridization of this carbon is sp2, right? Very good. How about this carbon in acetylene, this here? sp. About this? sp. Okay, good. Okay. Any question? Let's go to the next one. Okay. I want somebody to read this for me. Any volunteer? Yes, go ahead.
According to the various quantities on the bonded orbitals, the CH4 is independent, which geometry below is the carbon atom.
Okay, how many of you did this? Okay, so let us see. Can we do this together? So we have to indicate the geometry of this carbon here, and also to show the bonding orbitals. Okay, so let us draw the structure first. You have carbon bonded to 4 hydrogen atoms. Okay. Okay, now, what is the hybridization of this carbon? sp3. So therefore, let us draw an sp3 carbon first, right? So we have this carbon here. Okay, now I'm going to draw sp3 hybridized orbital. Because that carbon wants to bond to 4 different atoms, it will undergo hybridization, so that all of those orbitals will now be sp3 hybridized, and the bond angle, and this bond angle here will be, what will it be? 109 exactly, 109.5 degrees. The same thing here, 109.5 degrees. The same thing here, 109.5 degrees, and the same thing here. So the geometry of that central carbon atom will be what? A tetrahedron. Now, okay, but that is not the complete question. The question is to draw the bonding orbitals. Okay? So let me take this out. We know that carbon is going to be the sp3 carbon. So we have drawn the sp3, the orbitals on that carbon atom. Now, let us now have the hydrogen. What kind of orbitals will hydrogen use? S. Hydrogen does not need hybridization. Okay, so it just comes with S. Hydrogen is here. Come with S. Hydrogen is here. Come with S. Hydrogen is here. Come with S. Hydrogen is here. So each one of those has, you now have bonding orbitals, the 2 electrons, 1 electron from the s orbital of hydrogen, and 1 from the sp3 hybridized orbital from carbon. So now you have those 2 electrons now are under the control of the 2 nuclei. The same thing here, you have 2 electrons here. You have 2 electrons here. You have 2 electrons here. And now, this is what we call a sigma bond. This is what we call a sigma bond. With the designation using the Greek symbol, delta. Now, the sigma bond is a head-to-head overlap of atomic orbitals to form bonding orbitals. Keep that in mind. Sigma bond, head-to-head overlap. Head to head overlap of atomic orbitals to form a bond. Okay, so now we have, therefore in this molecule here in methane, how many sigma bonds do we have? 4. We have 4 sigma bonds in methane. Okay, so the answer to this question is we have shown the bonding orbitals. The carbon is using the sp3 hybrid orbital, and hydrogen is using the s orbital. And then the geometry will be tetrahedral, which will be this here. Because what is happening, this carbon here is sitting in the middle of a tetrahedron, okay, in which all of these bond angles are 109 degrees. All of these 109 degrees, okay? And that is the nature of an sp3 hybridized carbon atom. Okay, so let us do the last one. Is there any question on that? Okay, okay, Jocelyn, was that you who read the last one for us? Okay, any volunteer to read this last one? Number 4. Somebody to read number 4 for us? Yes, go ahead. What's your name?
Tiffany.
Oh, Tiffany. Okay, go ahead.
Calculate the molecular weight of the compound below.
Okay, very good. Okay, calculate the molecular weight of the compound below. This was a slightly tricky question, wasn't it? But it's not that it's not that tricky. Well, because I'm asking for molecular weight. Most of you probably thinking of molecular formula, right? So it wasn't tricky. That's good. Okay, that's good. I'm glad you know that. Okay, so what's the answer to this? Okay, how do we approach it? How do we approach this question here? Yes. Yes. Okay. This is a carbon, right? The end of a line is a carbon. The intersection of two lines, the intersection of two or more lines is a carbon, right? Yes. Yes, right. Okay, so at the end, okay, let us do this. Let us do this. So what do you have? So you say this is CH3, right? And you say this is CH3. Very good. Okay, so the first thing we do is to write the molecular formula, right? So what would be the molecular formula for this molecule? C8. Where did you get the 8? Let's start counting. Let's start counting from here. 1, carbon number 1, right? 2, 3, 4, 5, 6, 7, and carbon number 8. So that's C8. Okay, so far so good. About the hydrogens. H. How many hydrogens? 16. Very good. Okay, 16. So how did you get 16? You have 3, right? That is 4. There's 1 here. So that makes it 4, right? You have 2 here. So that's 5, 6, 7, 8, 9, right? 10, 11, 12, 13, right? And is that right? 16. Okay. Okay, so once you get the molecular formula right, which is this here, then what do you do to get the molecular weight? Find the atomic weight. So for carbon, the atomic weight of carbon is 12. So for carbon, so we have 8 times 12, and that is what? 96. And then you have 16 hydrogen. So 16 hydrogen, and that gives you 16. And what is that? 112 grams per mole. Okay, how many people got that right? Okay, very good. Okay, the question number 3 and 4 are 4 points each, and question number 1 and 2 are 2 points each. Okay, so I will give you back your papers on Thursday. And there will be another short quiz on Thursday on chapter 1 also. Okay. Okay, so at this point, any question? Yes, go ahead. Oh, the H's, the hydrogens? Okay. Okay, let me take this eraser out of here. Okay, I'm going to put the hydrogens there, okay? Hydrogen here, you see that? Because carbon must have 4 bonds, has a valence of 4. You have 2 hydrogen here, 2 hydrogen here, 1 hydrogen here, 2 hydrogen here, and 2 hydrogen here. Now, if you count those hydrogens, you find 16 hydrogens. Okay. What this question is actually just testing is your knowledge of valence, essentially. Okay, at this point, what I want to do now, before we go to the hybridization that I promised you on sp2 hybridization, I want to show you how to write organic chemical structures. Okay, so let us say writing organic chemical structures. Writing organic chemical structures. Let us start with this molecule here. I call it molecule butane, which has a formula of C4H10. That is the formula for that molecule called butane, which is one of the components of your cooking gas. Now the formula is this here. The structure is this here, this here, this here. Keep in mind, each bond is represented by a line. This line here represents a bond. This here, this, this, this. We have 4 carbons, so we need to show all of the 4 carbons. This we call a Kekulé structure. Or your book also called this line bond structure. Okay? You can either call that a Kekulé structure or line bond structure. And for the Kekulé structure, what do? We represent each covalent bond with a line. And then you show all of the atoms. We also have another representation that we could write. We could have this carbon is here, carbon is here, carbon is here, carbon is here. How many carbon? That is 4. Okay, so now we have hydrogen, 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 this we call a Lewis structure. So you could tell, this is the last time I'm going to write a Lewis structure. This is absolute waste of time. so anyway, but you need to know that that is a Lewis structure. And what is a Lewis structure? In the Lewis structure, you simply use the dots to indicate each one of the electrons, the valence electron that is used in bonding. In this case, rather than using a line, you have 2 electrons here, which is used to bond between this carbon and this carbon. So you simply use a dot to represent the bonding. 2 dots represent 1 covalent bond, and then you show all of the atoms that are involved. Okay. Moving forward, we will not encourage you to use the Lewis structure. It does take too much time. Okay. We could also have now. If I now take a look at this here. Now I want to write what we call a semi-condensed structure. With the semi-condensed structure, I will take a look at this carbon. Say this carbon is attached to this hydrogen, this hydrogen, this hydrogen. So I will write CH3. Notice I have the hydrogen comes after the carbon. Then I will then draw a line to show that this carbon is attached to this carbon. To show that bond, the covalent bond. Then I'll take a look at this carbon here, hydrogen, hydrogen. So that is a CH2. This one is another CH2 with a bond to the carbon-carbon bond. And finally, I have this carbon bonded to this. I will show that bond. And then you have a CH3 right here. This we call the semi-condensed structure. That is the semi-condensed structure. Now we could even condense this structure further. Instead of showing the bond between the carbon atoms, I could simply remove that bond and then have this CH3, CH2, CH2. What happened to my pen here? My pen is going crazy. Okay, so we have CH3, CH2. Notice you do not show any bonding, covalent bonding. CH2, this is the condensed structure. This is a condensed structure. Okay, very often we will be using condensed, semi-condensed, and sometimes the calculate structure. And finally, we have another structure, which we call the skeletal structure. Now, in the skeletal structure, what we do, we simply now take, we say this carbon here, we draw a line. We have this carbon at the end. The intersection of a bond of a line of 2 lines is a carbon, then this here. So we have how many carbon? 1, 2, 3, 4. That is the skeletal structure. So depending on what we are doing at any given time, we may find the skeletal structure very useful indeed. In the skeletal structure, the end of the line is a carbon atom. At this point, since you know about valence, you know that carbon must have 4 bonds, so you do not show any of the hydrogen or the carbon atoms. You simply assume that those hydrogen must be there. Okay, the intersection of 2 lines is a carbon atom. Keep in mind that you must obey the valence rule. And the same thing here, carbon here, and then the end is here. Okay, so those are the 4 basic representations that we use to write organic structure. So let us do a few more examples on this. Okay, now supposing I have this. Supposing I have this. Okay. Can you write a skeletal structure for that molecule? What kind of structure is that anyway? Semi-condensed. Okay. Semi-condensed. Okay, can you write a skeletal structure for that? Okay, it's a little tricky also. Okay. Okay, so the skeletal structure we have, what is it? How many member ring do we have? 6 member ring, okay? It's a 6 member ring. It's a 6 member ring. And then here, we have oxygen attached. In the skeletal structure, you do not show the carbon atom, you do not show the hydrogen atom, but you have to show the heteroatom, what we call the heteroatoms. The heteroatoms are those atoms that are not carbon or hydrogen. Everything else is an heteroatom. Yes. Also, you show the hydrogen that is attached to the heteroatom. Was that your question? Okay. Okay, in the skeletal structure, you do not show carbon, you do not show hydrogen, but if you have an heteroatom, you must show it. If an hydrogen is attached to an heteroatom, you must also show it. Okay, so this would be the skeletal structure for this molecule right here. Do you follow that? Yes. Say that again. Mm-hmm. Or it could be in any form. It could be. Yes. Right. For example, if I ask you, supposing I ask you to give the skeleton for this, just a minute. Yes, go ahead. Why do I do what? Oh, why did I remove the hydrogen? Which hydrogen? Oh, this here. Because there's hydrogen attached to this oxygen. Yes, that's what I said. If the hydrogen is attached to an heteroatom, you must show it. Okay. What will be the skeletal structure for this molecule here? Let us draw the skeletal structure for this molecule here. Okay, what will it be? How many member ring? 5. 5-member ring, okay? So you want to draw a 5-member ring, right? You draw a 5-member ring, okay? And where it will be the attachment? Right here? Okay? Okay? Right? Right? And Na2, right? Exactly. Okay, because this carbon here is this carbon, right? This carbon here is this carbon, right? And of course, you see the nitrogen. You must show the nitrogen and the hydrogen attached to it. Yes.
Okay, so when you join the, that side line, does it matter if you go up or down first? Or
It doesn't matter. It doesn't matter. Yes. Yes. Okay. Okay. Yeah. That is a different question. Now, if the question is if you are given the molecular formula, how will you be able to write the structure? I don't think that there's for any given molecular formula, there are several structures you could write for it. So at this point, I will not ask you that question. But when we get to that, we're going to get to that in chapter 3. Okay. But if I give you, I could write, in this case, I could give you a structure in one form, and say give it to me in another form. That's what this is. Okay. Yes. Yeah, no, go ahead.
Okay, in the last structure that you used, you had the O and the H separated. In this one, you have NH2 together. Is that still the same thing? Is it still the same skeleton?
Yeah, it's the same. It's just a condensed form of Na2. That's all.
So if you were to ask us for the skeleton structure and we gave you the condensed form of the NH2 at the end, it would still be correct?
Yeah, it will be fine. Right. Okay. Now let me ask you another question. Supposing, what time do we have? Oh, we got plenty of time. Oh, good. Okay. So, supposing I give you this molecule here, C4, H4, right? And I say this molecule here has 4 sp2 hybridized carbon. It has 4 sp2 carbon. It has 4 sp2 carbon. This is the formula right here. Can you give me the structure? Now what we are trying to get you to do now is to think critically. Give me the structure of that molecule, keeping in mind all of the valence rule and the octet rule. It has 4 sp2 hybridized carbon. Give me the structure. Can anybody give me the framework of the structure? Yes, Mohammed? 4 double bonds. Okay. In a chain? Huh? 2 double bonds in a chain? Okay, let's see. Is this what you mean? Is this what you mean? We have 4 carbon, right? Okay, is that what you mean? Okay, let us look at the formula that we have. Keep in mind, this is the formula you have, C4H4. The formula that you have given me now has how many hydrogens? 6. So it cannot be this. 3 double bonds. Okay, let me direct your mind in a different way. Okay. Yeah. Okay. Let me say this. Carbon has the ability of forming a ring. Okay, think that in that direction. Carbon has the ability of forming a ring. Oh, okay, okay. Okay, so it has to be. There is no other way to do it. Because if you follow all of the valence rules and the octet, you have one hydrogen here, one hydrogen here, one hydrogen here, one hydrogen here. That is the only way you could meet the valence and the octet rule using this formula here. No other way.
So why can't you do it as zigzag?
Which one?
Like the way we did before.
Okay. Which one? Which one?
When we have a zigzag, like, yeah.
Zigzag. Okay, we have 4 carbons now, right? Okay. Zigzag.
But I mean, I'm asking like, why couldn't you do it that way?
But you see, the requirement is you must meet this requirement. The molecular formula is C4H4.
Okay.
If you do it any other way, you have too many hydrogens in there.
So it has to be like pH, it would be like pH2 factor same like that. Okay.
No, it will not work. Oh yes, right.
But why can't you just like keep it how it is up there?
Okay, just a minute. Do you want me to keep it like this?
No. If you make it pH2,
Where? Which one?
no, just start all over.
Oh, start all over. Okay. Okay, very good. CH2.
pH2,
Mm.
double bond,
Okay.
double bond C,
Okay.
double bond C,
Double bond C. Okay.
yeah. Double bond C,
Double bond C again.
yeah. And then double bond CH2.
Double bond C. Okay, we have so far you have 4 carbons. We have 4 carbons already. 1, 2, 3, 4. H2 right here.
But they're not all hybrid. Yeah, 4 hydrogen.
Okay.
Are sp2.
Okay. 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 Very good. Very good. But that is wrong. Very good try, though. No, I like your thinking. That is the kind of thinking. That is the kind of thinking I want. Seriously. No, that is no. We want you to think critically. Okay. Let us look at what you have. What you have is a good one, right? Okay. The question is, what is the hybridization of this carbon here? What is this? sp2. What is the hybridization of this carbon? sp. But we told you that we have 4 sp2 carbons. This is sp. No, the number of atoms it is bonded to. Okay. So this is sp2. You see that? Do you see that though? You see it now? Okay. Okay, so the key is a triple bond. A triple bond depending on the molecule. If you have this here, just a minute. If I have this, okay, what is the hybridization of this carbon? Yes, it's sp. Okay, this is sp. This is also sp. Okay, you follow that? So this is the kind of thinking that you guys need to engage in. Yes. To do what? Did I? Oh, I do have another question for you. I have another question for you. Supposing I say I have a molecule that has the formula C4H5, 1 nitrogen and 1 oxygen, right? And I also tell you that the skeleton, the frame, structural frame for that molecule is this here. If I tell you this is the frame, the structural frame for the molecule, indeed, I could simply just give you this here, okay? And I tell you to give me the complete calculate structure, okay? Supposing I just give you this molecule here, the way it is written right here, it is just the structural frame, and I say, give me the complete calculate structure. What would that be? This is the molecular formula right here. Of course, this molecular formula I got from this frame. Yes. I say what? Okay. Okay. So now let us.
Okay, so is that not line bond structure? That's what I hear.
Which one is that?
Is that not?
Oh, this one here. Yeah, this will be your line bond structure if everything is correct. Okay, but what I want now, give me the complete structure. Okay, yes. Okay, very good, very good. I think now you are thinking. Okay, because the way this molecule is written, it is not a complete structure, right? So what I want you to do now is to complete that structure for me. So what do we do? Following the valence and octet. Let's start with this carbon here. Okay, does this carbon have the valence? Okay, so carbon is okay about the octet. So this carbon is happy, right? About this carbon, does it have valence? No. It needs how many more? One. About this oxygen, the valence is not met. So, okay, so it needs one more. So, why don't you simply place a double bond here? So now, is this carbon happy, valence-wise? About the octet. Just a minute. About this relation to the carbon, the octet, okay? So the carbon is happy. About oxygen, valence, okay? What's the valence of oxygen? 2. Valence. 2. The maximum number of bonds is 2, right? Is he happy with valence? About the octet. Okay, what does he need? No, octet. How many electrons does he have surrounding it right now? 4. So he needs 4 more. So therefore, he needs 2 pairs. So he needs 2 pairs of non-bonding electrons in order to satisfy the octet. Okay? Okay, so oxygen is happy now. About this carbon? Carbon is happy? About this carbon? No. What is wrong with this carbon? Valence? No. It needs 2 more bonds, right? Okay, you say it needs 2 more bonds? Okay, so is that right? Okay. So this carbon is happy valence-wise, right? Is it happy octet-wise? Okay. About nitrogen? What does it meet the valence? Is the valence okay? What's the valence of nitrogen? 3. Valence is different from valence electrons. Do not confuse that, okay? Valence is different from valence electrons. Valence is the number of electrons that it needs in order to become an octet. Valence electron is the number of electrons that it has in its outermost shell. Okay. Okay. So therefore, About with the respect to octet, nitrogen, what does it need? How many electrons does it have surrounding it now? 6. Okay, so therefore it need this, right? So therefore, this will be your complete calculate structure. Or line bond structure. Yes.
I just wanted to repeat what you said. You said that before you added the 2 extra electrons, that the valence was okay, but the valence electrons wasn't?
Valence for which one?
For nitrogen, before you added the 2 extra.
No, I did not say the valence. The valence, yeah, the valence was okay. But the octet, keep in mind, both of them, you need to satisfy both of those. The valence and then the octet. The valence is the number of bonds that it needs in order to satisfy the octet. Octet does it have 8 electrons around it? Okay? Okay, so now this will be your complete calculate structure. So the point here is, whenever you are giving structures like this, you need to be aware that each atom must satisfy its valence, thus also must satisfy the octet rule. Those are the guiding principles when you are writing these structures. What time do we have? Oh, you got plenty of time. Okay, so now let me give you one more question. Are you ready for this one question, right? One more question. Supposing I give you this molecule here, C2H6 with nitrogen. That is the molecular formula. Okay, what I want each one of you to do now is to use this formula here. Let me know whether this formula belongs to any stable molecule. In other words, can you make a stable molecule out of this formula? Can you make a stable molecule out of this formula? Okay, just take 1 second. Okay, you could start by joining 2 carbons or joining carbon, nitrogen, it doesn't really matter. Can you make a stable molecule out of this formula? You say no? You say no because you know that was what I was getting after. You just guessed it. Okay, what it is, yeah, you are correct, it is no, but why? Okay. Okay, what did you try to do? What did you try to do? Let's do it together. Okay, okay, what did you do? Okay, you join 2 carbons? And then the nitrogen at the end? Okay. The hydrogens? Because you only have 6 hydrogens, right? And then the other hydrogen goes to nitrogen, right? Okay. Okay. This carbon is happy, right? This carbon is happy. About this carbon is happy, right? About nitrogen, it's not happy. So what does it need? Is the valence right? Is the valence right? No. Is the octet right? No. Okay. So what can we do? Can we do anything to help it? It wouldn't work. It would not work. Okay. It would not work. So therefore, this here does not belong to any stable molecule. So you begin to see the kind of question you are going to be getting, right? You have to think in terms of working these problems out. And so when you go to R, I know some of you are already doing the problem set in R. You'll find this kind of problem set in R. So I will advise that each one of you should actually take advantage of working those problems. It's not time yet. We still got 5 more minutes. 4 more minutes. That's plenty of time, right? Okay, but no, seriously though. All I want to do now is just wrap up the chapter 1. We finish chapter 1. When we come back on Thursday, we are going to start with chapter 2. No, but before you go, no, don't go yet. We still got time. You guys are trying to take my time from me. Okay. Okay. Remember, I promised you that, right? You don't want to do that anymore. You know about sp2 carbon now. This molecule here, this is an sp2 carbon, right? You all know that, right? Okay, and we know that the bond angle here is 120 degrees. The same thing here. So in other words, this is what we call a trigonal planar geometry, because the molecule is essentially flat. Okay? It's essentially flat. And of course, one of the bonds that you have here, one of these bonds, we call this a pi bond. And of course, one of these is a sigma bond. Okay, so you know that already. So let us move on. What I just want to do is just to summarize the chapter for you. Of course, you see here, this is the hybridization for the sp2 carbon. You see, in this case, you have the 2px orbital, another 2px orbital, mixing with an s orbital. So these three orbitals here, they mix together to form the three sp2 hybrid orbitals. This here, and this here. And the last p orbital that is not used, and that is this one here. Okay, that is what the carbon now uses to form what we call a pi bond. It is what you see in the next slide. Okay? Okay, so you see this carbon here and this carbon here. The pi bond is a side-to-side overlap of the p orbitals, and that's why you get the pi bond. So anyway, at this point, I think we have finished chapter 1. The same thing happens with sp hybridized carbon. So if you have the time, take some time to read up on this in your book. And also the same thing happens with your other heteroatoms like oxygen and nitrogen. They also go through hybridization. So we'll see you on Thursday. Yes.
So when we're talking about billing, the billing number, I think, and I guess the best question on the name, like through the octet. I'm confused like how you see